All right. Hello, everybody. In this little section, we're going to be talking about 3D forces. And basically, it's the exact same thing as what we've already covered with 2D forces. The only difference is in 3D space, we're adding this extra Z component. And so we're going to spend today on the idea of breaking that force down into components and adding resultants like we did the first 2 days when we were covering 2D vectors. And then next time we'll talk about equilibrium. So I drew this ahead of time so I didn't have to waste too much time. If I had some kind of force in this 3D space, the idea is I want to resolve this red vector into these three components where I can see this little fx and an fy and an fz, which are the projections of that vector onto that axis. And I can actually see how that would project straight over to the y-axis and down to this other plane, this xz plane, if I knew this angle theta sub y that's shown there. So usually this isn't the case. This is kind of rare, but it may come about where you know the angles, but you may not know the distances, this x2, y2, z2. So let's talk about both. When you know the angles, the basic process is the first step would be I want to take this f and resolve it into my horizontal and the y direction. And I can see I kind of drew out this plane, that little gray plane. It's like a 2D plane, and I can think of that f being a triangle on that plane with this theta sub y being the angle to the y axis. So if that's true, then I know that the magnitude of the force in the y direction would just be equal to the total force times the cosine of theta y. Now I wouldn't take that as a guaranteed equation you can always use, but in this case I can see that the theta sub y is the adjacent to the component fy, so I would use the cosine in that case. What then I can do is that would give me my fy, and I'm done with the fy. If I were to take the sine of that force, it would give me what I'm calling f sub h. That fh down here is like the horizontal piece of it. It's not along the x or z axis, but it gives us the in the xz plane what the magnitude of that horizontal vector is. So once I have that last step would be I have to break that horizontal into x and y direction. So the last step would be that my force along the x direction would equal this force, this horizontal force, times the cosine of what I'm calling angle phi. So now I'm looking in this xz face with this green, and I can see I have this triangle, and I'm projecting it onto the x, and that is my adjacent angle. So I have the cosine, and in the z direction, I know that's equal to this horizontal force times the sine of that angle phi. And of course, I could have done that from the get-go and say that, therefore, if I were to go all the way from the total force, I know that in the x direction it would be times the sine theta y times the cosine of phi, or this one would be times the sine of theta y times the sine of phi. Something like that. More likely than not, or what you should really be familiar with, is the other case where what we know are these points. So we know where this vector is starting, this x1, y1, z1, and I know where that vector is ending, x2, y2, z2. I know the distances. So when the distances and lengths of these vectors or forces are known, I'm going to follow the exact same process I did in 2D. So the total distance in the x direction would just be the differences between the x1 and x2 if I'm not starting at the origin. Same idea with the y direction and the z direction, z2 minus z1. And if I know the distance that this vector travels, or the magnitude in the x, y, and z, I could find the total length of this vector, and that's just equal to, from Pythagorean, only in 3D, I have dx squared plus dy squared plus dz squared. So I have that extra term in there. From that, what I would do is to get to my component form, It's the same idea that I did in 2D. So the force component in the x direction is equal to the total force times the magnitude of the distance in the x direction over the total distance of the vector. And same with the y and the z. And I could work backwards and actually solve for my angles. Once again, this is something I don't think is as important. I rarely would see this, but you could say if you wanted to find some kind of angle to the x-axis, that'd be equal to the distance x over d, and the cosine theta to the y would be equal to dy over d. Cosine theta z is equal to dz over dz over d. So, like I said, not as important. This is really what you want to focus on. It means that the general process would be that the first step would be to find the length of that vector f based on how far its distances in the x, y, and z. Then I can break it into component form. So let's take a look at a short example of how I would use this angle piece, and then I will use a separate video, I think, to actually do an example for what we'll more commonly do. But if I were to look at this and I have a 900 Newton vector and I'm given the 65 degrees this time to the horizontal and this 20 degrees to the z-axis, really it's just a matter of looking about where these angles are to, or what's my reference point here. If I'm trying to find the x, y, and z components of this 900 Newton force, the first thing I would say is, well, I could find my y direction directly. That's just equal to 900. In this case, it's the sine of 65. I know up above I said it would be cosine for that y, but in this case I'm given the angle down to that horizontal. So you're always thinking, what's the angle in reference to? If I want, in this case, the y component and the angle is to the x, then it's going to be sine, because I want the opposite, over here somewhere. And then, of course, the other component to that vector would be the horizontal. So that'd be 900 times the cosine of 65. Oh, man. It's going crazy. Times the cosine of 65, and that gives me something like what? 380.36 newtons. Now that doesn't really do anything for us. It says intermediary, so from there I can find my force in the x is equal to the horizontal force times the sine of this phi, or this 20 degrees, right? So 380.36 times the sine of 20, and now that gives me 130.1 newtons. But similar to what we did before, if I look at what this actually is, this x, I am going to manually put in a negative sign here. The reason I'm putting in that negative sign is because I can see that it's pointing in the x direction. Instead of resolving it back to any other direction, I'm just saying, look, it's pointing in the x. I use those angles. I can visually see how it would work. The last one I need to do is in the z direction. I can see that the resultant is pointing in the positive z direction, so I don't have to add a negative sign. So this is that horizontal, the 380.36 now times the cosine of 20, and if I punch it into my calculator right, I got 357.4 newtons. So that's kind of how you can break it down to find the magnitude of each component. Of course, from here you could also work backwards and find the magnitude of the force to prove it's 900 if I were given those three magnitudes, or find the angle. So I hope that was helpful. Like I said, I'm going to have a second video that will talk more about how we're going to add these vectors together, or the addition of these vectors in 3D space. So tune into that, and thanks for watching.